After we have our Cisco Catalyst switches configured, there are going to be times where things don't work perfectly. We need to know how to troubleshoot a switched infrastructure. And later on, when we get into routing, we'll make this more complex and start adding routers into the mix. But right now, we'll keep it fairly simple, just a couple of Cisco Catalyst switches connected back to back. And let's imagine that there is no communication between these switches. We've got a PC connected to one switch, a server connected to another switch, possibly, and they're not able to talk to one another. Or maybe the communication is slow. What are some things we can do? One of the first things we might want to try to do is to isolate the problem. One of the ways that I would start out is to see if we have connectivity between the switches. Notice that the switches have management IP addresses. What if we did a ping? We could ping from one switch to the other, or attempt to ping from one switch to the other, and see if that was successful. We'll take a look at that in the live interface in just a moment. But a couple of other things we could do to help isolate the problem: swap out the cable. If the switches are in close proximity with one another, maybe just swapping out the cable can give us a different result. Or maybe moving the cable from one port on one switch to another port on that switch, to see if there's an issue with the port. There could be something wrong with the port configuration in terms of speed or duplex settings. We'll be talking about that in the next couple of videos. And as we start to examine one of the switches, we might determine that it doesn't boot up correctly. Maybe there's an issue with the switch. We could swap out the switch. So again, to sum up, as we start to isolate the issue, we could see, is it an issue with connectivity between the switches? Can the management IP address on one switch ping the management IP address on the other switch? What if we swapped cables? What if we swapped ports? What if we swapped switches? Those are some things we could try, but the first thing I'm going to be trying in the real world is I'm going to do a ping to see if I can get from one switch to the other. Let's go to the live interface and take a look. We're on switch SW1 right now, and if we want to see if we have network connectivity with another switch, we could do this. We could say ping, P-I-N-G, followed by the IP address of the remote switch. In this case, the remote switch has an IP address of 192.168.1.12. We press enter, and notice the information we get. We get a series of 5 exclamation points. An exclamation point is a good thing when it comes to a ping. That tells us that we sent out an ICMP echo. That's the protocol that ping uses, ICMP. We sent out an echo, and the exclamation points, or some people refer to those as a bang, we received 5 echo replies. That means that we have round-trip connectivity with this other switch. And speaking of round-trip, we can see what the round-trip time was. Is it working but really slow, perhaps? Look at this. We can take a look at the minimum round-trip delay, the average, and the maximum round-trip delay out of these 5 ICMP echoes that we sent. It looks like our fastest round trip was only 1 millisecond. Our longest round trip was 8 milliseconds, and on average, we had about a 2 millisecond round trip delay. Generally, anything under 10 milliseconds is considered to be a good thing. I'm not going to be concerned about any of these numbers. And we also see, thanks to the 5 exclamation points, that we've got a 100% success rate. 5 out of 5 messages made it there. I want to set your mind at ease about something that might happen, though. When you do your first ping, it's not uncommon for that first ping to time out. You might get a period showing up instead of an exclamation point in this very first position. And the rest work, but the first one times out. Don't be overly concerned. Just issue the ping again. What's probably happening if you get a dot for your first ping response, what's probably happening is that your switch didn't know the MAC address of the IP address that you were pinging. I said ping 192.168.1.12. Well, what if my switch didn't know the MAC address of that IP address? It wouldn't know how to properly form a layer 2 frame. So what does it do? It would send out an ARP message, an ARP broadcast, ARP, that's Address Resolution Protocol. That's a broadcast message saying, hey, can somebody tell me the MAC address that corresponds to this IP address? The other switch responds and says, yeah, that's me, and here's my MAC address. And as a result, switch SW1 adds the MAC address corresponding to 192.168.1.12, and it's able to properly form a layer 2 frame. It takes some time to do that, and that might make this first ICMP echo timeout. In fact, let's see if we can make that happen. We could do this. We could say clear out our ARP cache. I'm going to say clear ARP cache. That's where the MAC address to IP address mappings are stored. I've cleared that out, and by default, when we do a ping, there's a 2-second timeout before we give up and say, that's not going to work, let's try another ping or another ICMP echo. I'm going to reduce that timeout to 1 second instead of 2 to try to make the first one fail. Here's how we do it. It's called an extended ping. We just type in ping without an IP address, and it gives us a series of prompts. Yes, I want to use the IP protocol. My target address is 192.168.1.12. The repeat count is still going to be 5. The datagram size is going to be 100 bytes. Here's what I want to change. Instead of a 2-second timeout, just so we can see if the first one will fail, now that we've cleared our ARP cache, I'm going to make the timeout just 1 second. I don't want to do any extended commands right now or sweep a range of sizes. Ah, yes, look at this. The first one failed. Does that mean that we have a connectivity issue between these two switches? Probably not. Let's do another ping. I'll do a ping 192.168.1.12. 100% success that time. Again, the first one failed, not because of a network connectivity issue. It's simply that this switch had to send out an ARP and get an ARP reply before it could form that layer 2 frame to send the ICMP echo to the other switch. That took time, and the first one timed out. It did not indicate a network failure as evidenced by the rest of the ICMP echoes being successful, and then a subsequent ping was 100% successful. As we continue our look at how to troubleshoot a Cisco Catalyst switch, let's take a look at one of the most powerful tools that we have in our toolbox. It is the Show Interfaces command. Generally, we'll specify an interface after this command. I could press enter right now, and it would give me detailed information about the current status of every single interface, and that takes a while. So normally we'll want to focus our efforts and say, show me information about this specific interface. On SW1, the interface that's being used to trunk up to SW2 is interface Fast Ethernet 1/0/2. Let's take a look at that interface. What I want to draw your attention to right now is the interface status. It's this first line of the output. It says that this interface is up, and it also says the line protocol is up, and it tells us that that means connected. This first part, the interface status that is currently up, that refers to layer 1 of the OSL model. This is talking about the hardware. This can let us know whether or not we are receiving a carrier detect signal from the far end of this link. Let's move up to layer 2 and take a look at the line protocol. We can think of this as the data link layer status. And this lets us know if keep alives are being received at the data link layer. When an interface is up and operational, we refer to it as being in the up state. But we could have other combinations. Maybe we're up, down, maybe we're down, maybe we're administratively down. Let's take a look at some of the different options we have. When we're interpreting output from the Show Interfaces command, remember we're looking at layer 1 and layer 2 status, and that's going to give us information about the link status. In the example we just saw, we were up at layer 1, we were up at layer 2. That indicated to us that our link status was functional. What if we were up down though? Up down means that we're up and happy at layer 1, but we're not at layer 2. In other words, layer 2 keep alives are not being received. We've got some sort of a connection issue. If we're down, and that second down, the layer 2 down, in parentheses says not connect, that's telling us that something's not plugged in. Maybe our side of the cable plugged into our switch is not plugged in, or maybe the far end of the cable is not plugged into the far end switch. Or maybe the switches are connected physically, but the far end switch has that port at the far end of this link. That port is administratively shut down on the other switch. That's a possibility. If we're down, then that means that we're not happy at layer 1. We've got some sort of a layer 1 hardware, an interface issue. We could administratively shut down a switch port. For security purposes, that might be a good thing to do. so somebody doesn't just find an open switch port and connect into it. And we're not done taking a look at the show interfaces command. In our next video, we'll take a look at how we can interpret some of the statistical information seen in this command. But in this video, let's take a look at one other command. It's the show interface status command. Let's go back out to the live interface to check it out. Let's take a look at the output of show interfaces status. This is going to give us some very important information. Not only does it tell us whether or not a port is connected or not. You see, here's our trunk port going up to switch SW2. It's connected. We see that it's a trunk. If it's not a trunk, if it's an access port, we can see if that port is a member of a specific VLAN. We can see that this port is a member of VLAN 1, for example. But one of the main things I wanted to show you in this output, one of the main things I'll use this command for, is it tells us the duplex and speed settings. This is a major reason why we might have connectivity issues between our switches. The duplexes and the speeds are not matching up on both sides of the link. What are we running here? The A tells me that I auto-negotiated the setting. In other words, I did not statically hard code that we're running in full duplex. I did not statically say that we're running at 100 megabits per second. The A's tell me that these were auto-negotiated. And auto-negotiation can let us down sometimes. Let me demonstrate what I'm talking about. Let's go over to switch SW2. Let's check out its interface status. We'll do a show interface status on SW2. And the far end of the trunk link, it's coming in to gigabit 0/10. Notice that the duplex is set to auto and full, and the speed is set to 100. Let me show you a really common issue that is not that intuitive. I don't think it's that intuitive why this would happen, but it sure can happen. If we have one side of a link set to full duplex and the other side of the link is set to auto duplex, I think it's reasonable to assume that, well, one side is set to full, the other side is set to auto. The auto side will simply see that the other side is full duplex and it will become full. That's what auto is all about, isn't it? Negotiating with the far end. Here's what a lot of people don't understand. If we're set to full duplex on our Cisco Catalyst switch, we are not going to be participating in auto negotiation. Let's prove it. Let's, on switch SW2, let's go into interface gigabit 0/10, and instead of setting it to auto duplex, I'm going to hard code it to full. Let's say duplex full. By saying that, I'm saying that that port is not going to be participating in the negotiation of duplex. Let's go to the other side and see what's going on. Notice that we're getting a duplex mismatch error right now. It says the far side is set to half duplex. We hard-coded ourselves to full. Why would the other side do half duplex? Let's go check it out. We're getting an error message here on screen. If we do a show interface status, we can see that even though we told this side to auto-negotiate duplex and we hard-coded the other side, auto-negotiation just failed. Here's what happened. We set SW1, this switch, to auto-negotiate. We hard-coded the other switch to full duplex. Full duplex does not participate in auto-negotiation, and what happened when this switch tried to auto-negotiate with the far end? Since the other end was not participating, this switch defaulted to half duplex. We now have a duplex mismatch. And with the duplex mismatch, traffic still gets through somewhat, but it can significantly degrade performance. You might not even notice that you have an issue for a little while, and then your users start complaining that things are really slow. It's taking 30 minutes to transfer a file. It should take 1 minute. My printer is working really slow. Those conditions could be indicative of a duplex mismatch. You can quickly check your duplex status, again, by simply saying show interfaces status, and you definitely want to stay away from setting one side of a link to full duplex and the other side to auto duplex.